Hello, I would like to welcome you to Lecture 30 of 3N03. This will be our last lecture in this course. We'll discuss the concept of multi-stage amplifiers, how to use more than one stage in building an amplifier, and how to analyze them. We'll discuss the concept of the loading effect and how you take this into account when you calculate the gain of a stage, and then we'll give some examples. In many cases, we are interested in not only using one stage of an amplifier, using multiple stages. For example, one stage may not be sufficient to give you the gain you're looking for. Maybe this AV1, this voltage gain here is not sufficient. And you need to get a higher gain. So you have to cascade the number of these stages together. Other reasons for that we already discussed is the case when we had a common collector followed by a common emitter followed by a common collector amplifier. And the reason we do this cascade is that the common collector has a very high input resistance and very low output resistance, but the common emitter gives a very good gain. So when we cascade these three stages, we're able to combine these good characteristics: very high input resistance, very high gain, very low output resistance. Now, if you cascade the number of these amplifier stages and we assume there is no loading, the assumption of no loading assumes that when you connect one stage to the next stage, the gain of this stage is not affected by the following stage, is not being loaded by that stage. And this will happen in one of two cases. Either the output resistance of the first stage is very small, very close to zero, or the input resistance of the second stage is very high, I would say approaches infinity. Okay, so here if I have this first stage, the second stage, either the output resistance from here is zero, meaning all the amplified voltage will appear across the input resistance of the second stage, or if the second stage has an infinite input resistance regardless of the output resistance of the first one. If this is the case that we have for the cascade, then we can simply say the total voltage gain is the product of the individual voltage gains assuming no loading. But in most realistic cases, however, there is some sort of loading. This loading may be little or maybe much, but we have to take it into account in our calculations. So the ideal scenario, if this one alone gives you a gain of minus 100, this one gives you a gain of minus 100, when you multiply them together, you get a gain, or when you cascade them together, you get a gain of 10,000. But in reality, the gain that you're going to be getting will be less than 10,000 because of one of them, the second stage loading the first stage, say. To understand the concept of loading, we take a look at this diagram that we did already consider during this course. This is the first amplifier, this is the second amplifier. Any voltage amplifier can be represented by this equivalent circuit. We have an input resistance, there is some input voltage appearing across the stage. This input voltage, we call it VN1, is what's going to be amplified by this voltage controlled voltage source. And then there is an output resistance, and this is what appears at the output of the first stage. If this first stage is not connected to anything else, then you are going to be measuring V output, which is equal to AV multiplied by Vn. But if you connect it to a second stage, what's going to be happening is that the voltage appearing at the input of the second stage is really a voltage divider between Rin2 and Rout1. So what was amplified by the first stage may not all appear across the input of the second stage. So what the input here to the second stage will be the amplified voltage multiplied by Rin2 over Rout1. The ideal case, as I said, either Rout1 is 0, and in that case there is no voltage division, or Rin2 is very high, approaching infinity, and in that case all the voltage will appear across Rin2 regardless of Rout1. And of course in the second stage, the voltage appearing across the input resistance of second stage will also be amplified, and then you have an output resistance. Now what you're going to be measuring here as an output voltage is again a voltage divider between the load resistance and the output resistance. This is why we always prefer Rout to be as small as possible, so that we can connect any load without causing much drop in the gain. So you have to, it has to be very clear in your minds that when you design a circuit, you are not assuming there is a load. The result may be different if you load it with some load resistance as shown here. It may be different because of this voltage division property that's happening. Now, for most modern amplifiers, well-designed amplifiers, the input resistance usually in the mega ohm range, and the output resistance usually between 50 to 100 ohms, which is very little. So these are almost near ideal conditions, and in that case, we can assume that the voltage, the total gain, is the product of the gain of the first one and the gain of the gain of the second one. We call these the standalone gains. Gains assuming that there is no loading. Okay, but in many cases, in other applications, when there is significant loading, you can calculate certain gain, but when you load your circuit, you get a completely different measurement as a result of the loading effect. Okay, let's take a look at an example here. We have 3 common emitter amplifiers are cascaded. Each stage gives a gain of minus 30. It has an input resistance of 0.5 kilo ohm and output resistance of 0.25 kilo ohm. So 500 ohm input resistance, 250 ohm output resistance. Find the gain, input resistance, and the output resistance of the 3-stage amplifier. So what we did here, we cascaded 3 amplifiers, common emitter amplifiers. Each one of them gives a gain of minus 30. They have an input resistance 500 ohm, output resistance of 250 ohm. Would like to find the total gain. This gain here, which is reported, this is called the standalone gain. It assumes there is no loading. It is in the same way we have been calculating these gains for the common emitter, common collector, and so on. But if you are not, well, you are loading the first stage by the second stage, and you are loading the second stage by the third stage. And we didn't say anything about the third stage, so we assume that it's not connected to a load on the other side. We didn't say anything about the impedance of the source, so we assume that the impedance of the source is 0. Okay, but of course, if this is given, then you have to take this into account into your calculations. So this is how circuit here looks like. We have the first stage, this is our first stage here, and then the second stage, and then the third stage. Okay, the first stage, you see the input resistance, the voltage controlled voltage source, and then the output resistance, R output 1, and then for the second stage you have Rn2, and then you have AV multiplied by Vn2, and then you have R out 1, and then for the third stage you have the input resistance, voltage controlled voltage source, and then the output resistance. I didn't say anything about the load, so you can assume that it's open circuit, there is no loading here. I didn't say anything about the source, so you can assume that the source does not have a source resistance. If there is a source resistance here, then the voltage appearing across the input resistance of the first amplifier, first stage, is really a voltage division between this Rn1 and the source resistance. But here this wasn't given, so I can assume all the source voltage will appear across the input resistance of the first stage. So now we have to calculate each one of them separately. The voltage appearing here, Vn1, is simply equal to Vs, and this is what I say here. There is no voltage division. Now this amplifier will amplify it, and then you get the voltage between here and here, between these two terminals, is the gain of the first stage multiplied by Vn1. And now you have a voltage division between the output resistance of the first stage and the input resistance of the second stage. So you get this voltage ratio. This is AV multiplied by Vs, and if you don't mind, I dropped the subscript 1, 2, and 3 from the gain, because the gain here is the same for all of them. So this is what's coming out from this voltage controlled voltage source, and then you have voltage division. So Rn2 over Rn2 plus R out 1, and this is what I have here. Okay, the gain of the first stage is minus 30. The input resistance of second stage 500 ohm. The output resistance of the first stage is 0.25 kilo ohm. So 0.5 kilo ohm and 0.25 kilo ohm. So this will give you a ratio of 2 over 3 by minus 30. So you get minus 20 volts. So what's appearing here at the input of the second stage is minus 20 multiplied by Vs. So the voltage is amplified by 20, but there is a phase shift of 180 degrees. Now we move from this here to the output, to the input of the third stage. This minus 20 volts will be also amplified, so it will be multiplied by another minus 30. This will give us the voltage here. And then you have a voltage division between the input of the third stage and the output of the second stage. Input resistance of the third stage and the output resistance of the second stage. So you multiply this one here by minus 30 to get the voltage here. And then you multiply by 0.5 over 0.5 plus 0.25. So now we calculate the input to the third stage. As I said, we already have this one here. This will be also amplified by minus 30. You multiply by 0.5 or 0.5 plus 0.25k. You end up, this will give us 2 over 3 multiplied by minus 30, you get minus 20. So minus 20 by minus 20 end up by 400 Vs. So this is the input to the third stage. And because the third stage is not loaded, the voltage appearing at the output will be equal to this input voltage by multiplied by minus 30. So you multiply this by minus 30, you get minus 12,000 Vs. So whatever you put at the input of the three-stage amplifier will be amplified by 12,000 as an amplitude, but will be a phase shift of 180 degrees. Now I would like you to compare this number to the number that we would obtain if we multiply the three gains. So the three gains should give us here minus 30 by minus 30 by another minus 30. So this should give us 27,000. But we didn't get 27,000. Why? Because we have loading effect. So the total gain that you got was not minus 27,000, you got only minus 12,000. So loading effect does reduce the gain. You can see here, looking at the input of this three-stage amplifier, we see the input resistance of the first stage, which is 0.5k. Looking from the output of the third stage, we see the output of the third stage amplifier, which is 0.25k. So here you see the input of the first stage as your input resistance, and the output of the last stage is your output resistance. And the gain is simply, as you can see, we took into account the loading effect here. So we have seen how can by knowing the standalone gain, by knowing the input resistance and the output resistance of each stage, we can calculate the total gain and the input resistance and output resistance of the total cascaded stages. Now if you have loading, and I'm here to talk about the case where you have transistors now. We'll get into actual circuits. You have to calculate your gain by taking into account the loading effect. You have to see how the different resistances that you use in calculating your gain expression would change if you have cascaded stages. And now we have two different approaches. The first one is, if I give you, say, 3 common emitter stages, calculate the gain for each one of them standalone, calculate its input resistance, calculate its output resistance, and then use the equivalent circuit model I used in the previous example to get the total gain. This is one approach. The second approach is to determine what will be the effective, say, collector resistance or effective emitter resistance that using calculating your gain, and you calculate it directly, and then you multiply the three gains. You don't take into account loading anymore because you already took it into account when you calculated each individual gain. So now we have two different approaches, and both should give you exactly the same answer. Either neglect the loading completely, calculate the gain of the first stage, gain of the second stage, gain of the third stage, calculate the input and output resistances, and then use the equivalent model I taught you earlier. So this is the first approach. Second approach is no, you take the loading into account for every stage. So you see how the effective collector resistance will be, how the effective emitter resistance will be, and use this to calculate your own gain expression. Okay, I'm showing you here a number of possible cascaded amplifiers, and there are actually many topologies or many configurations used. This one here is a cascade between a common emitter amplifier. You can see the gain, the input is applied to the base. The emitter here is grounded in AC through this capacitor, and then the output is taken from the collector. So the input is between the base and the emitter, the output is between collector and the emitter. It's called a common emitter amplifier. What comes out from this amplifier will be amplified again through the stage, which is really a common collector stage. You can see the collector is connected to VCC, so in the case of AC analysis, it's going to be ground. So the input is applied between base and collector. The output is taken between emitter and collector because the collector is now ground. Now, when I calculate the gain of this stage, you can see this stage is being loaded by this other stage. I have two different approaches. The first one is simply ignore the loading completely, calculate the input and the output resistances, and then use the equivalent model I've shown you earlier. Input resistance, voltage controlled voltage source, output resistance. Or, as can be seen here, I can simply say that looking into this stage, I see some equivalent base resistance, R in base 2. Okay? So you can see between this point and the ground, I see some equivalent resistance. And this resistance is in parallel with the collector resistance here, with the 5.6 kilo ohm. So when I calculate the gain for this stage, I can take into account that the effective collector resistance is not 5.6 kilo ohm anymore. It's 5.6 kilo ohm in parallel with the input, the resistance seen into the base of the second transistor. And we did calculate that actually in a number of examples. It's equal to beta multiplied by RE dash. We did do this calculation. Okay? And if you go through a number of examples we calculated, you see that looking into the base, the input resistance is approximately equal to beta multiplied by R in dash. Okay, so we'll this is for the case for certain topology. For this one, you have to put your own equivalent model and then try to see what is the resistance you see looking into here. You have to assume, of course, you put your voltage current source and then try to get the ratio between V base to I base. Anyway, so there is some value for this one here. We know we can get it for any configuration of the transistor. And this one here, in this case, this resistance to ground is in parallel with R collector, which is 5.6 kilo ohm. If I calculate things that way, then my gain is simply the product of the first one multiplied by the product of the second one. And then I already took the loading into account. I don't have to take it into account again. This is the second configuration, and this one is using the book of Floyd. This is a common emitter amplifier. You can see the emitter is connected to ground in AC analysis. And this is another common emitter amplifier. And they are called the AC coupled. AC coupled because I'm connecting the output from the first stage to the input of the second stage through a capacitor. So that the bias point of this circuit is independent of the bias point of this circuit. Because this capacitor is open circuit in DC, so this can have any operating point, this can have any operating point. And there are amplifiers called DC coupled. You take the output directly into the input without a capacitor. But this means that the operating point of the second stage will affect and will be affected by the operating point of the first stage. Okay, they affect one another. The operating points will not be independent. So here in the same concept I put earlier, you have to find, there are two approaches for solving this problem. Either you calculate the gain of this one independently, assuming no loading. Calculate the gain of this one independently, assuming no loading. Use the equivalent circuit model, input resistance, gain, output resistance, and then you determine the total gain. Or, when you calculate the gain of this stage, you take into account loading. So what are the effective collector resistance here? Is not this RC1. No, because you can see in AC analysis, this point will be also connected to ground with this resistance. This point will be connected to ground with this resistance as well. And then not only that, you have also the resistance that you'll see looking into the base of the second stage, R in base 2. So in that case, the effective collector resistance here that you can use in calculating your gain is RC1 in parallel with RB1 in parallel with RB2 in parallel with R in base 2. So you can imagine there is another resistance connected between here to ground. It represents the effective resistance looking into the base. So now it's not only this RC1, so I call this one here RC1. It's not only this one here, this is called RC1. I have this R1 as well in parallel. I have this R2 as well in parallel, and I have R in base. All of them will give you the effective collector resistance of the first stage. Okay, so if I calculate the gain that way, then I can simply say that the gain of these two stages is the product of the first one, which I already take loading into account, multiplied by the product of the second one. Now take a look at the second stage. Second stage, you have RC2 here, and you have the load resistance. So effectively, between the collector and the ground, I see RC2 and I see RL. So the effective collector resistance here is really the parallel combination of these two. So you can calculate the effective gain of this stage as well. Okay? If you have done this, if you calculate this one this way, you calculated the gain here this way, then the total gain is their product, because you already took the gain took the loading into account. Okay, I'm showing you one more configuration for cascade amplifier. This is called DC coupled. You can see the output from the first stage goes directly to the input of the second stage. Then the bias point of this stage is determined by the bias point of this stage. Okay, in addition to AC analysis, of course, AC signals are passed to the base of this one and so on. This one will have its own advantages. Maybe it's better to get to make it to make the bias point here more centered relative to VCC. There are some advantages for these configurations. Each one of them has its own advantage and disadvantage, but this is also a possibility that can be used for cascading amplifiers. Okay, this is a configuration that the book of Floyd focused on. These are two common emitter amplifiers, and as I said, you have two possible, and they are actually AC coupled. So AC coupling means the bias points will be independent, the DC analysis will be independent, but in AC the second stage loads the first stage, and the resistance seen between the collector and ground is not R3 only, it's R3 in parallel with R5, in parallel with R6, in parallel with R in base 2. All these will be in parallel, as you could see here, and you should use them when you calculate your gain. We did calculate the gain for this stage before, and the gain for this stage was equal to the collector resistance divided by RE dash. So here I'm going to say RE1 dash. So this RC is not 4.7 kilo ohm anymore. If you take loading into account, it's going to be 4.7 kilo ohm in parallel with this one, in parallel with this one, in parallel with R in base, which I can find through the DC through the analysis. By knowing the operating point, I can find this input resistance. We did find it before actually for this configuration when this is shorted to ground, and as I said, it was equal to beta RE dash. We did find it for common emitter amplifiers, it's beta RE dash. Second stage here is not loaded. For this topology is not loaded, because you could see there is no other load resistance connected here. Then there is no resistance in parallel with R7. Then I don't have to worry about loading for the second stage. Only the first stage is being loaded by the second stage. So for AC analysis for the first stage, this is how really things look like. This is the collector resistance we had originally, but in parallel with it, we have the input resistance of the second stage. You see, input resistance is a parallel combination of R5, R6, and Rn looking into the base of the second stage. Okay, so you see what happened? This calculation, as a result, reduced the effective collector resistance, which is a parallel combination of these four, from 4.7 kilo ohm to only 1.63 kilo ohm. And this, of course, if you have RE dash, which was calculated for this example, to be 23.8, this reduces your gain from 4.7K divided by 23, which will give you maybe 200, approximately 200, to only 68.5, because now we have less effective collector resistance. So you can see the effective loading reduces the actual gain of your amplifier. Okay, let's have one practical example. We have these are two-stage common emitter amplifiers. I'm giving you all the resistances here. 15 volts each one of them, 2.22k here, or 3.3k, 1k, 5k. This one here, let's see, this is 1 kilo ohm, this is 2.5 kilo ohm, this is 15k, this 5k, and the second stage is loaded with a 10 kilo ohm. So when I calculate the gain of the second stage, I have to take into account that. I will follow the second approach. I will not calculate the standalone gain, the input resistance, the output resistance, and then use an equivalent model to calculate my gain. No, I will let you do this. I will calculate the actual gain with loading. Okay, so here the effective collector resistance of the first stage is 5k in parallel with 15k in parallel with 2.5k in parallel with the input resistance looking into the base of the second stage. And the effective collector resistance here is 5k in parallel with the load resistance, which is 10k. So if I calculate this way, I can calculate AV1, the effective gain of the first stage. I can calculate AV2, the effective gain of the second stage, and then the total gain is their product. So we'll calculate the gain of the first stage, the gain of the second stage, and then we'll calculate the overall gain. So let's see how we should proceed. But of course, we have first to find the operating point. This is how we go about calculating the gain, the input resistance, the output resistance for amplifiers. First, the operating point. From the operating point, you determine the parameters of your AC model. Here we have RE dash for each one of them, RE1 dash, RE2 dash, and then we start to calculate the gain. We have already the expression for the gain. It is RC over RE dash, effective collector resistance for RE dash. So I have first to find RE dash for each one of them. I will focus on the second stage, because the second stage is the one that loads the first stage. So first calculate the operating point for the second stage and then move from that point. If you do the same for the first stage, you'll see that RE1 dash is 19.8 ohm. Okay, so this one here has units of ohm, of course. Now, looking into the base of the second stage is very important to us, and we did calculate that in a number of examples. The impedance seen looking into the base is equal to beta EC multiplied by RE2 dash. This number is very important because this is one of the resistances that load the output of the first stage. We already have beta EC, it's given us 200. We already calculated RE2 dash 17.4 from the last slide. You multiply them, you end up by 3.48 kilo ohm. Then the input resistance of the second stage. The input resistance of the second stage, and if you remember, the second stage looks something like this. If you can draw the road through here, it looks something like this. The second stage, this was grounded. We have this collector resistance here. We have a load resistance, and this AC. I'm showing here AC analysis. Okay, this AC here. This one we have this resistance here. We have this resistance here. Okay, so we can try to draw this one here again. So I have this ground. So looking into the second stage, I see three resistances in parallel. I see this resistance, and I see this resistance, and I see the input resistance looking into the base. And this is what I wrote here, that this input resistance seen looking into the second stage is 15k in parallel with 2.5k in parallel with this input resistance of the base, if you which is 3.48. If you calculate all the three, get 1.33 kilo ohm. Why is this number very important? Because this is what loads the collector of the first stage. So now, the collector of the first stage sees this input resistance in parallel with its collector resistance. So if you want to calculate the effective gain of the first stage, we have to take this one into account. So this is how the first stage really looks like. We have all the resistances and so on. We have the source. And now, connected in parallel to the first stage, we see the input resistance of the second stage we already calculated earlier. So the effective collector resistance that you use in calculating your gain expression is RC1 in parallel with Zn. Because remember, this one is connected between the collector and the ground. This one is connected between the collector and the ground. So here, this is the equivalent collector resistance, 1.04K. So the collector resistance went down from 5K to 1.05K. This means that the gain of this stage will be reduced to only 20% approximately of its original value. Because the gain of this stage, if you remember, is simply given by this expression. It is the effective collector resistance divided by RE1 dash. But this number went down from 5K to only 1.05K. So the gain drops dramatically due to the loading effect. So now we can calculate the gain of this stage. We divide this number by RE1 dash, which we calculated earlier, and we know the gain of the first stage. So the gain of the first stage, the effective resistance of the first stage divided by RE1 dash. This one we calculated 1.05K over 19.8, you get only 53. And of course here I'm assuming that I'm taking into account that I didn't forget that this is a common emitter amplifier. So even though I write it that way, but I know that the gain is negative. There is a phase inversion of 180 degrees. Now we do exactly the same for the second stage. This is the second stage. It is being loaded by the load resistance. Then the effective resistance of the collector of the second stage is 5K in parallel with 10K. So this will result in reducing the value of this resistance from 5K to 3.3 kilo ohm. So the gain of the second stage is again given by this expression, the effective collector resistance divided by RE2 dash. RE2 dash 17.4, you get the gain of 191.4. So now what is the total gain of these two stages? Simply the product of these two. Okay, you simply multiply these two numbers and you gain your total gain. Of course, this is minus 191.4, this is minus 53, then the total gain will be positive. The second approach for calculating this is simply to ignore the loading completely. Calculate each one of them separately and then build the equivalent model. Input resistance, voltage controlled voltage source, output resistance, input resistance, voltage control voltage source, output resistance, and then find the total gain. And this should give you exactly the same answer that we got here, and I would encourage you to repeat these same steps using that approach. So the last thing that I would like to mention here is simply the total gain, as I said, is the product of the two gains, and this will give you 10,144. And as I repeated earlier, please repeat these same steps assuming standalone amplifiers with no loading, but you take into account the equivalent circuit model. Input resistance, voltage controlled voltage source, and then an output resistance, and then you cascade them. And then you have the source at the input stage, you have the load at the output stage, and then try to get the total gain. You should get exactly the same answer, 10,144 for this example.